In mathematics, real projective space, or RPN, is the topological space of lines passing through the origin 0 in Rn+1. It is a compact, smooth manifold of dimension n, and is a special case GR of a Grassmannian space. Basic properties. Construction. As with all projective spaces, RPN is formed by taking the quotient of Rn+1, 0, under the equivalence relation x lambda x for all real numbers lambda 0. For all x in Rn+1, 0, one can always find a lambda such that lambda x has norm 1. There are precisely two such lambda differing by sign. Thus RPN can also be formed by identifying antipodal points of the unit n-sphere, Sn, in Rn+1. One can further restrict to the upper hemisphere of Sn and merely identify antipodal points on the bounding equator. This shows that RPN is also equivalent to the closed n-dimensional disk, Dn, with antipodal points on the boundary, Dn equals Sn-1, identified. Low-dimensional examples. RP1 is called the real projective line, which is topologically equivalent to a circle. RP2 is called the real projective plane. This space cannot be embedded in R3. It can however be embedded in R4 and can be immersed in R3. The questions of embeddability and immersibility for projective n-space have been well studied. RP3 is so, hence admits a group structure. The covering map S3 RP3 is a map of groups spin SO, where spin is a Lie group that is the universal cover of SO. Topology. The antipodal map on the n-sphere generates a Z2 group action on Sn. As mentioned above, the orbit space for this action is RPN. This action is actually a covering space action giving Sn as a double cover of RPN. Since Sn is simply connected for n2, it also serves as the universal cover in these cases. It follows that the fundamental group of RPN is Z2 when n greater than 1. A generator for the fundamental group is the closed curve obtained by projecting any curve connecting antipodal points in Sn down to RPN. The projective n-space is compact connected and has a fundamental group isomorphic to the cyclic group of order 2. Its universal covering space is given by the antipody quotient map from the n-sphere, a simply connected space. It is a double cover. The antipode map on Rp has sign, so it is orientation preserving. IFFP is even. The orientation character is thus. The non-trivial loop in Act is on orientation, so RPN is orientable. IFFn+1 is even, i.e., n is odd. The projective n-space is in fact diffeomorphic to the submanifold of R2 consisting of all symmetric times matrices of trace 1 that are also idempotent. Linear transformations. Geometry of real projective spaces. Real projective space admits a constant positive scalar curvature metric, coming from the double cover by the standard round sphere. For the standard round metric, this has sectional curvature identically 1. In the standard round metric, the measure of projective space is exactly half the measure of the sphere. Smooth structure. Real projective spaces are smooth manifolds. On Sn, in homogeneous coordinates, consider the subset UI with Xi0. Each UI is homeomorphic to the open unit ball in Rn and the coordinate transition functions are smooth. This gives RPN a smooth structure. CW structure. Real projective space RPN admits a CW structure with one cell in every dimension. In homogeneous coordinates on Sn, the coordinate neighborhood U1 equals x10 can be identified with the interior of n-disk Dn. When Xi equals 0, one has RPN-1. Therefore the n-1 skeleton of RPN is RPN-1, and the attaching map F. Sn-1 RPN-1 is the 2-to-1 covering map. One can put induction shows that RPN is a CW complex with one cell in every dimension up to n. The cells are Schubert cells, as on the flag manifold. That is, take a complete flag 0 equals V0 less than V1 less than Vn, then the closed case cell is lines that lie in Vk. Also the open K cell is lines in VK1. In homogeneous coordinates, the cells are. This is not a regular CW structure, as the attaching maps are 2 to 1. However, its cover is a regular CW structure on the sphere, with 2 cells in every dimension, indeed, the minimal regular CW structure on the sphere. In light of the smooth structure, the existence of a Morse function would show Rpn is a CW complex. One such function is given by, in homogeneous coordinates, on each neighborhood UI. G has non-degenerate critical point where 1 occurs in the ith position with Morse index I. This shows Rpn is a CW complex with 1 cell in every dimension. Tautological bundles. Real projective space has a natural line bundle over it, called the tautological bundle. More precisely, this is called the tautological subbundle, and there is also a dual n-dimensional bundle called the tautological quotient bundle. Algebraic topology of real projective spaces. Homotopy groups. The higher homotopy groups of Rpn are exactly the higher homotopy groups of Sn, via the long exact sequence on homotopy associated to a fibration. Explicitly, the fiber bundle is. You might also write this as or by analogy with complex projective space. The homotopy groups are homology. The cellular chain complex associated to the above CW structure has 1 cell in each dimension 0. For each dimensional k, the boundary maps dk. Delta decay Rpk-1, Rpk-2 is the map that collapses the equator on Sk-1 and then identifies antipodal points. In odd dimensions, this has degree 0. Thus the integral homology as Rpn is orientable IFFn is odd, as the above homology calculation shows. Infinite real projective space. The infinite real projective space is constructed as the direct limit or union of the finite projective spaces. This space is classifying space of O, the first orthogonal group. The double cover of this space is the infinite sphere, which is contractible. The infinite projective space is therefore the Ellenberg-MacLane space K. For each non-negative integer Q, the modulo 2 homology group, its cohomology ring modulo 2 is where is the first Stiefel-Whitney class. It is the free algebra on which has degree 1.